So in this video, we're going to look at how to actually go through the full method of substitution to solve a system. And you're going to see step one is exactly what we just practiced in the first video. You need one of the equations to be solved for one of the variables. So it's okay if the equation says y equals, like we saw up top. It's also okay if it says x equals. Either way, we know we're going to replace a variable with what it's equivalent to. Um, so you're going to see in example one, that's not the case. We'll have to decide for ourselves which variable we want to get by itself. And if you can recall from systems in the past, actually this system is not the the best for substitution. We have a different method we'll see next time called elimination, but the goal today is to practice substitution. So we're going to go ahead and try that. So according to step one, we'll solve one of these variables, solve one of these equations for a variable, and I would say solve one of them for the variable x because we won't need to divide by a coefficient to get x on its own. We'll either subtract this 4y or add the 5y. And then once we have that, we'll substitute like we practiced in the first video, and we'll solve. We'll just solve an equation, and once we do that, we'll use our result to then go ahead and find the value of the other variable. So let's go ahead and try an example of this so you can get an idea of what's going on. And in this first example, we are going to we're going to rewrite one of these equations. So when I work substitution method, there is work to be done with each of the equations. So the first thing I actually do is take each equation and write them separately, side by side, instead of this stacked format where one is above the other. So that's what I'll do first is I'll write one equation here and the other to the side of it. And now that I have these equations rewritten side by side, what I need to do is rewrite one of them to have a variable on its own. And again, the variable x is the easiest option here because the x has a coefficient of 1. It does not matter which x we get by itself in this situation. I would personally solve for the x in this equation to the right because we need to add 5y to the other side, which is going to give us more positive values than negatives, which is what would happen if we subtracted this 4y over here. So positive values are a little bit easier in our calculations. We're less likely to make an error. So over here, I'm going to add 5y to both sides to solve the equation for x. And so we add 5y to each side of the equation. And again, these are not like terms. We can't combine them, but we can write them together. And so these will cancel, and we're left with x equals positive 5y. That plus for positive 5y, negative 10 is now minus 10. So 5y minus 10. And at this point, we have x isolated over here, and we see that x is equal to this expression 5y minus 10. And what that tells us is that x can be interchanged with the expression 5y minus 10. X is equivalent to the expression 5y minus 10. And so you'll notice in this other equation that we have not yet used, there is a variable x over here, and this rule that we just found can be applied to this x as well. So if we know that x is equal to 5y minus 10, we're going to replace this x with that expression 5y minus 10. And now you'll see that we've replaced x with that expression, and we have an equation that only uses a single variable, the variable y, meaning we're able to solve this equation now for that variable by going through some steps that we already know. So I still use parentheses when I substitute. The good news is there's no value in front of the parentheses other than that understood 1. So we don't need to distribute in this scenario. We can go ahead and start to combine like terms. We have 5y plus 4y over here, and that gives us a total of 9y. We still have the minus 10, and on the right side, we are still equal to 26. And so we continue solving our equation. We'll add 10 to both sides of the equation, and we'll get 9y equals 36. And lastly, divide by 9 on each side of the equation, and we'll get y equals 4. And so in just a few steps, and we're solving an equation, just like we've done so many times in the past, and we're able to find a value of the variable without ever trying to graph an equation of a line. But like an equation of a line, the solution is an ordered pair. It's still this x, y coordinates that we could plot on a graph. And we know now that this point has a y value of 4, but we still need to know the x value. But now what we get to do is substitute again. Because if we know y is equal to 4, that means we can replace y with 4. And we have this other equation over here that we started with earlier, and it has a variable y, and so we can use this rule that y equals 4 over here for this y as well. And so now all we'll do is we'll substitute, and we'll be able to solve for x. So in here we're going to have x equals, and instead of 5 times y, we're going to replace that y with a value of 4. So we're going to have 5 times 4, and then we'll still have the minus 10. And very quickly here, we could calculate that. You can use the calculator that we've been using in class. 5 times 4 is 20, minus 10 is a value of 10. And so what we have now is the location of our solution. So if we had graphed these two lines, what we would have found is that they do intersect, and they would have intersected at a point that has an x value of 10 and a y value of 4. So we'll write our solution as an ordered pair 10, 4. And that would be the end of that process. So without graphing, we're still able to find the solution 10, 4 that satisfies both equations. If we were to replace x with 10 and y with 4, here we'd get that this is equal to 26. And if we did the same thing down here, replace x with 10 and a y with 4, we're going to get an end result of negative 10, which is what a solution should do. It should satisfy both equations that were given, because the solution is a point on both of the lines. All right, so we're going to take a look at another example here. And what's going to happen, we're going to see maybe a different outcome. It's very common to get a solution, but that is not always going to be the case. So in the second example here, we have two equations, and you'll see that we're not using x's and y's. This is using f and g's. You might see a's and b's, j's and k's. It doesn't really matter what variables we're using. Just a little side note here, when you write solutions, it's always based on alphabetical order. So as we solve this equation, if we get a solution, because f is before g in the alphabet, we'll put the f coordinate before the g coordinate. And so when we write our solution, we'll put the value of f first in that solution. But let's go ahead and look at this scenario. The kind of nice thing about it is one of the equations is already solved for a variable, the variable f. Maybe the not so nice thing is that we see some fractions here, but don't panic. We have a calculator that can help us with that. And it might turn out that in this equation, it's not going to be a big deal for us. But I'm still going to start the same way I normally do, is instead of having these equations stacked, I'm going to write them side by side so I can go through my steps for substitution. And now that I have these equations written side by side, I can look at if one of the equations has a variable is solved for a variable already. And we see that in the first equation, that is the case, that f is equal to the expression 6 minus 2g. And so there's that interchange again. We can replace the variable f with an expression that it's equivalent to. And so anywhere we see the variable f, we can replace it with the expression 6 minus 2g, which is what we'll do in this second equation over here. We have 1/6 f, and we'll instead have 1/6 times the expression 6 minus 2g. So let's go ahead and replace the variable f and put that expression inside parentheses. And so again, everything in the equation is staying the same. All we are doing is replacing a variable with what it is equal to, and that's what we have here. Now, these parentheses are reminding us to distribute our fraction of 1/6. Either go through those steps on your own, or use a calculator to assist you. When I distribute 1/6, 1/6 times 6 is going to be equal to 1. 1/6 times negative 2g, that 1/6 times the negative 2, the 2 multiplies to the top of the fraction. That's going to give us a value of negative 2 over 6, which reduces to negative 1/3. So we have negative 1/3 g, but over here we have positive 1/3 g. So we will keep that, and then the equation is still equal to 1. So you might be noticing right now we need to combine some like terms on the left side, and you might also notice that those two like terms are direct opposites of each other. We have negative 1/3 plus 1/3, and when you combine those, you're going to get an end result of 0. So there are some cases here where we actually lose our variable, and in this scenario, we get an equation of 1 is equal to 1. So anytime that we get to a point where we have an equation with no variable, we have to stop in and decide how to interpret that. Is it a true equation, or is it a false equation? And in this case, it says 1 is equal to 1. That is true. Both sides are equal in value. And so in the case where it's true, and it's always true, we are going to say that there are infinitely many solutions. That was also something that we had said when we graph. If there's a case where the equation is not true, such as 3 equals 1, that's never going to be true. That would be a case of no solution. But because we have a true statement, we are going to interpret that as infinitely many solutions. And what that means for us is that there is an infinite amount of solutions, but it does not mean every point that we can think of is a solution. It means there are a lot of ordered pairs that we can find that are going to work for both equations. And the reason for that is, if you recall from graphing, we have the same line twice. Both of these equations are actually the same. It is hard to see that in this scenario, but actually, if you were to rewrite this second equation here by canceling your fractions and moving the g term to the right side, you're going to get an equation that will say f equals 6 minus 2g. So we can get it through graphing by graphing the same line twice, but through substitution, we see it where the variable will eliminate, we get a true statement, and that's how we come to that conclusion for infinitely many solutions.